Welcome to the podcast on inverse functions. This is kind of a difficult topic, so I've divided the podcast into two parts. This is part one. You've actually used inverse functions since the first time you ever solved an equation. For example, if you had an addition equation like x plus 5 equals 6, the way you solved it was to reverse the addition operation of plus 5. You said minus 5 on both sides. X equals 1, and that's reversing or an inverse function that solved the problem. If you had a multiplication problem like 5x equals 10, the operation on x was multiplying, you reversed it by dividing. We call that an inverse, and you got x equals 2. So reversing operations has been around your math career for a long time. Now, when you write a function in its formula form, you have a series of operations. Like this function involves first multiplying by 2 and then adding 3. Can you find functions that reverse entire series of operations? Can you find inverse functions? Well, let's take a look at that. We've studied functions in different forms. We've seen functions as ordered pairs, we've seen functions as graphs, and here you're looking at function as a formula. Let's take a look at how you would find the inverse of a function in its ordered pair form. Suppose f of x is the function 3, 6, 5, 9, negative 4, 1. Now that's a function because to each first element there corresponds one and only one second element. And suppose we form a new function in a very simple way. We just take each ordered pair of f and we flip it around. So instead of 3, 6 we get 6, 3. Instead of 5, 9 we get 9, 5, etc. Notice that the domain of f, 3, 5, negative 4, becomes the range of g, 3, 5, negative 4. The range of f, 6, 9, 1, becomes the domain of g, etc. Do these reverse each other? Well, let's take a look at this through the composite function f composite g, and we'll evaluate f composite g at 9 and see what happens. If we're successfully, well, let's just see what happens. By definition, f dot g of 9 is f of g of 9. So think about it. What does g do to a 9? To see that, go into g, and it says here in the function, g changes a 9 to a 5. So we get f of 5. Well, what does f do to a 5? Well, you go up to the f function, and it says f takes a 5, and it changes it to a 9. So we end up, after operating on 9, with both f and g as being right back at 9 again. So whatever g did to 9, f reversed it and took us back to 9 again. Let's see if g is also the reverse of f. We'll try g of f of negative 4 and see what happens. That would be g of f of negative 4. And according to our rule for f takes a negative 4 and changes it to a 1. So the f of negative 4 becomes a 1. So now we have g of 1. Well, what does g do to 1? G takes a 1 and changes it right back to a negative 4. And so we see that it's very easy to get a reversing function by just reversing the ordered pairs in a function. Now, word of caution. Suppose there had been one more ordered pair here. Let's say negative 1, 6. This is still a function, because to every first element, there's one and only one second element. But when I reverse this last ordered pair to form g, something bad happens. The first ordered pair related the first element 6 with the second element 3. Now we have another first element 6 with negative 1, which means g is no longer a function. So in order for a function to have a reverse which is also a function, we need to eliminate this case. And what happened to us was to a second element 6, we had two different first elements, and so when we reversed that, we no longer had a function. So we need to add something to our definition of function to make it reversible or invertible, and we do that down here in this definition. A function that will have an inverse is called a one-to-one function, and we say a function is called one-to-one if for every first element x, there's one and only one second element y. Well, that's just the definition of a function. And for every second element y, there is one and only one first element x. That means that the reverse will also still be a function. Now, when we looked at graphs of functions, we could tell that the graph of a function was, or a graph was the graph of a function if it passed what we call the vertical line test. That is, if you drew a vertical line, it did not hit the function more than once. This second condition, to every second element there's one and only one first element, means in order to be one-to-one, functions must also pass a horizontal line test, because here's your second element y. It corresponds to two first elements, x here and x here. And so if a function is going to be one-to-one, if it's going to have an inverse, it has to pass both a vertical and a horizontal line test. This function doesn't, and so it does not have an inverse. However, suppose I erase the left side, so I get this function. It now passes the vertical line test. If I draw a vertical line test, I never hit it twice. If I draw a horizontal line, I never hit it twice, so this function would have an inverse. Now, down here I have a graph of a function. How would I graph its inverse? Well, I've marked some key points on the function, and I'm going to reverse their coordinates just like I did up at the top to get an inverse. So, and I'm going to do this in a different color to kind of keep it separate. Instead of 2, 3, the point on the inverse function would be 3, 2. So I'd go 3 to the right, 2 up, and get a point right here. 1, 1, of course, if you reverse it, it's still 1, 1. Negative 1, 0 would reverse to 0, negative 1. So that would be right here. And negative 2, negative 3 would reverse to negative 3, negative 2. So that would be right here. So my reversing function, my inverse function, would look like this. Now notice that there's a kind of symmetry there, and to see exactly what that symmetry is, we could draw a line that connected the points where the functions crossed. So I'd draw a line through here, and through here, and through here, and I'd get that line, and notice that along that line, when x is negative 3, y is negative 3. When x is negative 2, y is negative 2. When x is 1, y is 1. When x is 3, y is 3. Y and x are always equal along that line, so that is the line y equal x. So you can see that if you use y equals x as a mirror, this is a perfect mirror image of the original function to get the inverse. So let's go back now and do the inverse of our original example. We'll start off by drawing the line y equal x. We'll then locate some key points. This is the point 0, negative 1, so its inverse will have the point negative 1, 0 on it. Here it hits the line, so its inverse will hit the line. Here it ends up at 2, 3, so its inverse will end up at 3, 2. So if I draw the inverse of this function, I get this function. That's f of x. This is f inverse of x. Okay, so to get the inverse of a function, draw the line y equal x and reflect the original function on y equal x. And that completes the first podcast.